social collaborative filtering. And actually in this talk we have 2 universities in Hong Kong represented, also Michigan State University and JD.com. So long list of authors. Unfortunately, none of the authors could make it for this particular paper. So it's being presented by Wei-Wen Lu. So
good afternoon. This is Wei-Wen Liu from Chinese University of Hong Kong. And so this is not my work. Unfortunately, the first author cannot make it here this time, so I'm presenting on behalf of him. This is a joint work with City University of Hong Kong Data Science and Engineering Lab at Michigan State University, JD.com, and the Hong Kong Polytechnic University. So the name of the paper is called Social Rules. Sorry. It's called Deep Social Collaborative Filtering. So what is social organization? It is based on the simple idea that the information can actually propagate through social relations like co-workers or friends. That means that we're actually influenced, the user preferences are actually influenced by our friends and also our friends' friends. So people that share similar interests tend to get together and know each other and naturally form different communities like our RecSys community. So in this figure, we can detect 2 communities. On the left-hand side favor the drama movie more, while the right-hand side prefers the action movies. So with that said, the social relations can actually help us improve the performance of the recommender system. However, most of the existing social recommenders mainly focus on the direct neighbors, also known as the nearest neighbors. So, but actually, the neighbors that a few hops away may also contain rich information that can be utilized. This idea is based on the following 2 observations. The first one is that information is actually diffusing through our social relations, and like we talk to people, right? And second is that if we cannot get the information we want from our closest friend, we may seek out to our distant friends, also known as weak ties, for more information. So it makes more sense to consider both the distant direct neighbors and also the distant neighbors. So next problem is that if we're doing a specific recommendation task, like predicting how likely a user is interested in buying an iPhone 11 Pro, but actually not all the items that our friends interacted with are useful. For example, in this case, maybe just iPads and MacBook Pro that our friends may like or dislike are more important, rather than the books or t-shirts or the shoes. They are relatively unrelated. So our model needs to have the ability to find the most related items. So our next step is try to incorporate the opinions of our friends toward the related atoms into our model. So it is pretty simple that positive feedbacks and negative feedbacks from our friends influence our user preferences in different ways. So we need to deal with them separately. And by opinions, we mean that the ratings or reviews from our friends. So here is the overall network structure of this model. It consists of the four layers: the random walk layer, the embedding layer, the sequence learning layer, and the output layer. So for the random walk layer, it basically helps us to obtain the direct neighbors and distant neighbors. And we also try to rule out or filter out the unrelated atoms in this layer. For the embedding layer, we try to embed both user, atom, and ratings into continuous embedding space. And then for the sequence learning layer, we try to aggregate these embeddings, try to learn a unified representation of all the sequences and for the file prediction. For the random walk layer, we basically just use the random walk technique, try to generate the user sequences. For example, in this case, we start from U1 and we get the user sequence of U2, U3, U6, U7. It has a function that it can maintain the order of the users according to the distance to our target user. Here is the U1. And rather than directly use our user sequence, we propose to use the item-aware social sequence by associating an most related atom to each user by calculating the similarity between the atom that our user have interacted with and our target atom. So in our experiment, we just use the user atom interactions since the set information are not available in our dataset. So here is just an example. Let's do the movie representation together. And so we need to assign an atom for each neighbors. So for U2, clearly it just has one interaction, so we select V3. For U3, V5, U6, V5. But for U7, we have multiple user atom interactions, right? So we select the one that is most related, that is this one. That is how we generated the item-aware social sequences. And for the embedding layer, we just embed both user, rating, and atoms into continuous embedding space, and we deploy a fully connected neural network, GURV, and this take input of the concatenation of the three embedding vectors and output the so-called user-atom interaction embedding. And our next question would be how to extract features for each sequences and how to aggregate those embeddings for all the sequences. This is what exactly the sequence learning layer do. So inspired by the LSTM model, which can learn the representation for the sentences, so we regard the user atom interaction as the words and the whole sentence and the whole social sequences as sentences to learn the features for the sequences. And also use the hierarchical attention mechanism to assign weight for each interactions and each sequences. And for the upper layer, it's pretty simple. It's the two layers of fully connected neural network. And since our task is a prediction task, so we just use the most commonly used training loss, the mean square error loss. So here's just briefly introduce the experiments. So for this dataset shell, it contains user atom interactions, user-user connections, and also the ratings, which is the 5-star rating scheme. So you can see that we use the RMSES or evaluation matrix. You can see that our proposed DSCF model can achieve the best result, which demonstrates the effectiveness of our model. So just to recap, first, in this work, we designed a so-called deep social collaborative filtering model, and we generate atom-aware social sequences to consider both direct neighbors and distant neighbors, and we capture neighbors' opinions when doing the embedding, and we extract social features via the so-called LSTM with hierarchical attention mechanism. So that's pretty much all. And since I'm not the author of this paper, so I just try to deliver the big picture of this work. If you are interested in the detail of this paper, please directly contact the first author. Here is website and email.